So welcome everyone. So I'm Céline de Fouillois. I'm an application engineer at CAMECA, and I will be moderating today's event. So as you know from your invitation, we wanted to take advantage of the United Nations Women and Girls in Science Day, which was actually on the 11th of February, to celebrate female users of our CAMECA instruments all throughout the month. Just a few technical points before we get started. We have muted everyone for the time of the presentation to avoid any technical issues. But we do invite you to type your question in the Q&A interface, and we will answer them, Gina will answer them at the end of the presentation. During this Q&A session, you can also raise your hand via the Zoom feature and ask your question directly. We will unmute you one by one. So the talk is recorded and it will be made available on demand afterward. But the question session will be removed, so don't be shy to ask your questions. I am glad to introduce our speaker for today, Gina Greenidge from NPL. Gina will present her recent work on lithium-ion batteries using NanoSIMS. So Gina, it's your turn.
Thank you so much for the introduction, Celine, and thank you for the CAMECA team for inviting me to participate in their UN's International Day of Women and Girls in Science seminar series. So we had a talk about NanoSIMS last week, so this is slightly different in tech in that I am talking about using NanoSIMS to analyze carbon materials for next generation lithium-ion batteries. I work at the National Physical Laboratory, as Celine mentioned, which is right outside of central London and conveniently located right next to the airport. And we are the UK's National Metrology Institute, and we provide measurement services, measurement science, and engineering technology for research and for industry. And so I mentioned we're going to talk about lithium-ion batteries today, but why are they important? Well, as we race towards our net zero goals, electrification has a very important part to play in meeting our energy demands from grid and industry, and especially transportation. It's really vital that we get lithium-ion battery technology right to meet the coming demands. So the big picture challenges that we as scientists need to address when thinking about lithium-ion batteries are we need to improve the energy density, the cost, and the lifetime, as well as the safety. So commercial state-of-the-art lithium-ion batteries have a few major components. You have your anode, which is your negative electrode, a separator, and a cathode, which is your positive electrode, and these are separated electrically. Now, carbon materials are most widely used as the anode, and that is the material that we will be discussing today. And one of the major degradation modes of anode materials in lithium-ion batteries is the formation of the SEI, or the solid electrolyte interface. And this is a passivating layer that forms on the surface of the anode as a result of electrolyte degradation. Now, a stable SEI is important for battery performance. It actually helps prevent further electrolyte degradation, but the actual formation and instability of this layer is not well understood, and it actually varies depending on the electrolyte and the cycling conditions and the temperature, etc. So understanding the fundamental mechanisms that really cause the degradation of this layer is really important to optimizing battery performance. So here we have a little cartoon of the lithium-ion battery and the SEI layer. We have the orange, which is the copper carbon conductor. We have the black lines that act as the layers of the graphite, and we have some of the major components of the solid electrolyte interface, or the SEI, for example, LiO2 and LiF. So we have actually at NPL shown that there are different types of secondary ion mass spectrometry that can be used to study this layer. For example, we've used TOF-SIMS to detect SEI components as they vary with location and depth. So here, I'm just going to turn my pointer on. So here we see in a pristine material, we have C2H minus, which means that we have a lot of carbonaceous species in a pristine, which means uncycled electrode that has not been exposed to electrolyte. And then we have an increase in fluorine and phosphate ions, where in the uncycled anode material, which means it's been exposed to electrolyte and just cycled one time. And then as we increase the number of cycles, so you're aging your battery, you increase the fluorine. Now, this is a really good method for doing high throughput analyses and characterization and looking at large areas. But what we don't really see is very high detail and morphology in the material. So that led me to ask the question, how can we get spatial resolution and similar types of information? So that's where the NanoSIMS comes in, which is another surface analysis tool, but it's a nanoscale secondary ion mass spectrometer, and it has a spatial resolution of less than 50 nanometers. It also has a really good detection limit down to the ppb for some sample types, very high mass resolving power, and we can detect all elements, including hydrogen. Now, it is, of course, a lower throughput type of analysis. And since Cecile talked about NanoSIMS a bit last week, I won't go too much into detail about this, but we have a source, which is your cesium or oxygen primary beam, and we use some ion optics to direct the ion beam onto a sample where that energetic beam causes ionization, and then we can collect those secondary ions along the exact same optics, and then we pass it through another series of optics, and we separate these ions based on their mass to charge ratio. And in the NanoSIMS, we have 7 detectors, 6 of which are movable, and we can detect 7 secondary ion signals from the exact same analytical volume. And then we can raster over that sample, and then we can build up an image. And this characterization tool is destructive, so we'll remove one plane of material, and then we can analyze the plane beneath it. And from that, we can actually build up a series of images, as you will see. So the scientific questions I wanted to address using the NanoSIMS and lithium-ion batteries are, number one, can we spatially resolve the components of the SEI on graphite anodes in particular? Can we measure the depth of these components? And I will use the term depth very loosely because we don't have a quantitative depth. We just know how the components, the intensity of the components varies as we go through the successive surface layers. And how does the intensity of the relevant species change because of the aging that we see? And by aging, I mean cycling the battery multiple times. So these are some of the electrochemical details that were done. The electrochemistry was done by collaborator Teresa and Sinna at the University of Cambridge. So we have our anode materials, which consist of graphite, carbon black, a PVDF binder on copper foil. We use the electrolyte that contains lithium hexafluorophosphate, and she prepared a lithium graphite coin cell as pictured here. This is what it looks like, and this was all prepared in an argon glove box because lithium is very air and moisture sensitive. That will become important later. And then she cycled them at room temperature, constant current, and a C/20 rate, which means it was charged and discharged for 20 hours each. So this is a pretty slow cycling process. So for the NanoSIMS experimental details, we have a 16 kV impact energy, varying primary beam current of 0.5 to 2 picoamps. We have a high vacuum analysis chamber, so 2 by 10 to the minus 10 millibar. And I analyzed a series of masses from 12C, 16O, 12C7 lithium, as well as 12C19F. So the first challenge that I faced was, how do I transfer the samples that were delivered in some argon-sealed bags into the NanoSIMS, which currently does not have an air-free sample transfer system? So the first idea was to take a lecture bottle that consists of argon and create a shielding gas as I took the sample, which is this graphite and copper tape that I then stuck onto the sample mount. So can we do that under sealing gas and then mount into the NanoSIMS sample holder, and then or under the sealing gas as well, transfer it into the NanoSIMS chamber? And that did not work. It was very clumsy. There was lots of air exposure. So we decided that that wouldn't work. There would be too much degradation and exposure to air and moisture. So the next step was to do all of the preparation necessary to mount the samples inside of the argon glove box, which is a bit fumbly. The screws are very small and it's a bit challenging, but it was able to be done. And then after I assembled all of the samples inside of the glove box, I put it in a sealed bag, took it downstairs to the NanoSIMS, and then I was able to transfer the sample holder into the instrument in less than 90 seconds. So the second challenge that I had to address was because there isn't very much literature on the NanoSIMS analysis of lithium-ion battery materials, I had to build up my own library of mass spectra. So here I show some examples of high mass resolution spectra at mass 18 and mass 19. So at mass 18, we see a very clearly resolved 18O peak and a very clearly resolved 12C 6 lithium peak with very little overlap between the two peaks. And at mass 19, you see something very similar, a very clearly separated 19F, so a fluorine peak separated from a 12C 7 lithium peak. And we're also really surprised that we're able to see any lithium peaks with such good resolution and good intensity using the cesium beam. So now I get to show you what the images look like, the isotope images, after we selected the mass lines that we were interested in. So this is for a sample that was cycled only 3 times. So this is a very short number of cycles compared to what a usual lithium-ion battery lifetime is. And we see here we have a nice graphite flake, and then we have some of the other materials involved in the anode materials. For example, you have carbon black. But we look at first at this nice carbon flake, and we see that obviously 12C carbon. There's oxygen distributed with a few hot spots along this area. Not very much lithium, 12C7 lithium signal, just maybe in the corner here. And if we look at 19F7 lithium, we see that there is no 19F7 lithium on this basal plane, this flat area of the carbon surface, of the graphite surface, and similarly for 1331P. But again, we see it carbonaceous species on the surface of the basal plane. And this is on the bottom is the secondary electron image generated by the ions. And then we can also look at the isotope images generated for the sample cycle for 300 times, which is a much longer aging lifetime. And we can see, first of all, that we have a much higher lithium, 12C7 lithium signal distributed all over the sample. But again, we don't see very much 19F7 lithium on the basal plane on the surface, as well as 1331P on the surface. But we have carbonaceous species again all over the sample. So this is actually very good results because this corroborates previous data that says that the SCI on the cross section of the carbon materials is dominated by fluorine, and on the basal planes, these flat planes, are dominated by more organic materials. So then we can directly compare how does aging affect the intensities of the signals, and I chose to specifically look at 19F, 31P, and 12C7 lithium. So on the top row, we have samples that have been cycled for 3 cycles, and on the bottom row, we have 300 cycles. So this is a much longer aging time. So we have 12C, we see 12C all over, of course, but when we compare 19F 12C, for example, we see there's almost no 19F all over the sample surface and much significantly higher signal in the more aged sample. And we see similarly for 31 phosphorus, and we see very much the same types of increase in signal for 12C7 lithium. So as you age the cycle, we see that these SCI components in the layers grow within the sample. Now, because as I mentioned before, we can build up successive planes of images, we can create little GIFs that show what the sample varies like from the top surface as we remove successive layers. So on the left, we have the short cycle, 3 cycles, and we can see that we have very little fluorine on the surface and it goes away a little bit as we go through successive planes. But this effect becomes much more pronounced when we look at the sample that has been aged for a much longer time. So we have a lot of material on the surface, and as we go through the successive planes, we can actually see that we're removing those successive layers of fluorine on the surface. And we also did some SEM and EDS at the University of Manchester. So we looked at pristine anode material, and this is material that has not been exposed to any electrolyte and has not been cycled, and we see some carbon black, and we see these nice graphite layers as well, and we see the same recycled samples, and these were cycled for 3 times in electrolyte. And we wanted to compare what types of signal we get when we look at pristine versus cycled. So we see that for pristine, we see carbon all over, of course. And then for fluorine, we have some fluorine that is native in the material because of the binder. But we again see some fluorine starting to accumulate on the sample edges, but not much on the basal plane. We see a more distinct oxygen signal on the sample edges as well in the oxygen images. And we also see, especially with the fluorine, a much more increased signal of the phosphorus when we look at the sample that has been cycled. So this also correlates very well with the NanoSIMS images. And as I mentioned, we can do depth profiling, which is we can look at how the signal intensity varies as we remove successive layers. So we have here a sample that's been cycled 3 times, and if we're looking at just this region of interest on the basal plane, this nice flat graphite plane, and we look at the normalized intensity on the left-hand side, which is the y-axis, and then the planes are on the x-axis, we see that we have a decrease in the fluorine signal from the surface towards the bulk of the sample, and that's pretty much the same for most of the SEI components. And if we zoom in specifically to the fluorine on a linear scale, we can definitely see that this signal the decrease is more pronounced from the surface throughout the bulk of the material. Now we can also compare this type of depth profiling to this low number of cycles to the longer cycles. So we have 300 cycles here, and we can see immediately we have a much more increased fluorine signal, which corroborates well with the image data and the GIF that I just showed. And we also see a much more drastic decrease as well in the oxygen and the phosphorus signal, and just higher signals of lithium as well. So in summary, we can detect lithium molecular ions with very high mass resolution using the cesium beam. We have fluorine and phosphorus signals that are co-located on the cycle samples, and also they seem to not be depositing very strongly on the flat basal planes of the material. And each sample show increased lithium, phosphorus, and fluorine signals. So future work would be to continue developing that database or library of high mass resolution spectra so we can continue to study these materials. We can also analyze the cathode samples or cathode materials that are commonly used in lithium-ion batteries. We can also switch to the oxygen beam in the future to detect positive ions. And with that, I would like to thank, first and foremost, Teresa Insina of the Claire Gray Group at the Department of Chemistry in the University of Cambridge for providing samples as well as expertise, the NPL Explorers Award for funding this project, Dr. Greg McMahon, my supervisor, and Dr. Elizabeth Francis at the Royce Equipment Institute, the Royce Equipment Access Scheme at the Henry Royce Institute. And I'd be happy to take any questions.
Thank you, Gina, for this very interesting presentation. So
we already have one question, Celine.
Yes.
Two even.
So we actually have 2 questions. So the first one is, how have you measured the spatial resolution?
We have not measured the spatial resolution directly on these samples, but we do it on the instrument. from time to time when we would just want to confirm what the actual spatial resolution is using a line measurement.
And what kind of resolution are you at typically for those kind of analysis?
50 nanometers.
Okay. And the second question, can you estimate the depth in the depth profile? Did you do any sort of calibration?
No, we did not do any sort of calibration because the sample isn't very flat, so it would be difficult to take out the sample and then, for example, go to AFM and find the exact spot and figure the exact depth. We have discussed different mechanisms, for example, using a different type of SIMS where we know what the spotty yield is to try to estimate, but it still would not be specifically quantitative.
Mm-hmm.
Yes.
We also have a question from Carmen Ocean. Carmen, do you want to ask the question yourself?
Carmen, okay, I unlocked your sound if you want. That's...
Hi, Carmen.
Okay, well, I can ask Carmen's question then. So did you measure the 31 phosphorus and the 12C19 fluorine simultaneously?
Yes, I used combined analysis and they were very well defined separated peaks, so I was able to measure them using combined analysis mode.
Okay, so just some peak switching.
Yes, so I switched the peaks.
Okay, I guess you did the same for the fluorine
and the
19,
19
and C12-7 lithium.
Yeah.
And in that regard, did you take into account like any sort of tailing when you're measuring like the 12C7 lithium that is very low compared to the fluorine? Did you?
No, because they were so well defined and well separated that it was very distinct, so I didn't have to take into account any tailing.
Okay. So we have more questions. Are you able to identify the different products of battery life usage to understand the degradation of the battery with nanosims?
So if I can clarify the question.
I'm not completely sure what the, can you identify the different products, I guess, depending on what do you see an evolution of the different products?
Right, do I see different products depending on the aging?
Yeah.
So with nanosims, you have to know what you are looking for before you actually analyze the material. So you need to select which masses you're interested in advance. So it doesn't collect an entire spectrum. So I would have to know specifically what to look for, and that would probably have to come from a different technique like TOFSIMS, where someone says this appears upon aging that does not appear on a pristine material or a material that's not aged very long. And then I could look for it that way. But that would be difficult to identify using nanosims on its own.
Okay. We have a question from Hamad. Do you want to ask the question yourself, Hamad?
Hi.
Hi.
Actually, my question is, does the aged sample mean they have been analyzed or they were left without analysis over a long time?
Can you repeat that for me?
Referring to the aged sample, you said that they increased the concentration or the signal when they were analyzed. So do they have they been analyzed before? I mean, aged after being analyzed, or they were left without analysis over a long time?
Oh, yes. calendar aging versus cycling aging. So these were cycle aging, so they were not left for a long time. So I had some samples that were cycled for 3 times, and then some samples cycled for 300 times, and they were left for the same amount of time. So it wasn't a calendar aging type of just time degradation.
Okay, thank you.
Thank you. And one question from Eric Wood. Do you see different concentration of products at the grain boundaries?
Yes. Well, it's difficult to determine. We do see at the prismatic planes of the graphite, we do see that we have the presence or the absence of certain materials, but with nanosims there can be edge effects, so it's hard to say for certain if it's an edge effect or if it's an actual feature of the experimental conditions. So we're still doing some more work on them.
Thanks.
I think I actually missed the question. Is it possible to visualize inclusions in semiconductor by this method? I don't know if you can actually, if you have an answer for that.
What kinds of inclusions?
I don't know. Whoever has that, it's an anonymous question, so I don't know who has that question. Raise your hand if you want to give more precision about that question.
So we can look at semiconductors and we can visualize certain sizes, presumably.
Oh, okay. Someone has raised their hand, so Alexei. I just activated your sound if you want to.
Do you hear me?
Yes, we can hear you.
I would like to know whether it's possible to measure iron in indium phosphide. So we need to visualize small inclusions which are not measurable by optical methods.
Yeah, and what size of the inclusion?
It's a small inhomogeneity regions.
Yeah, I think if it's over 50 micron region, sorry, 50 nanometer region, around there, should be able to see it.
Thank you very much.
We also have a question from Ziad. Do you want to ask your question, Ziad?
Hello, everyone.
Hello.
Yes, thank you very much for the informative presentation. I have a question regarding the dendrite formation. Can we identify the dendrite formation on battery anode, lithium battery anode, using NanoSIMS method that mentioned? Thank you.
I haven't looked specifically into dendrite formation. And I'm not exactly sure what types of sizes those would be, the dendrites. But if it's in the order of magnitude that is reasonable to use the nanosims for, then yes, we could potentially see if we have just pure lithium, probably more likely using the oxygen beam than the cesium beam.
Sorry, I think you've mentioned like the minimum scale of measuring. I think it was like 50 nanometers or
about there.
Yeah. Oh. Thank you very much. Thank you.
You're welcome.
And we also have a question from Peter Noak. Do you want to answer, Peter?
Yes, can you hear me?
Yes, we can hear you.
Yeah.
Go ahead.
Thanks a lot for this nice presentation. I have a question that's more related to the lateral resolution. So would it be possible with this tool to actually map segregations and grain boundaries?
Yes.
Okay. Thank you.
And an additional question from Eric again. Do you want to ask your question? Yes.
Yes. Just briefly, at the level of lateral resolution that you were looking at, did you see any variation in the fluorine or the phosphate concentrations within a single grain, or was it just over multiple grains?
So within a single graphite flake, if I understand your question correctly, I didn't see, I can look at a single graphite flake on the surface of a single graphite flake. That was in the order of a few microns. Does that answer your question, or do you mean variation within that specific flake?
Yes, sorry. I was just wondering if you had done like a very high spatial resolution scan over one flake just to see if you could see any heterogeneity within one flake.
Within the flake?
Yeah.
No, I don't have anything that high resolution. I haven't done that yet.
Okay. Any more questions? I did have one question, Gina, regarding the sample transfer. So 90 seconds, that's actually impressive. But I guess it's still not perfect. So did you actually did some test or some analysis specifically to see what were the surface changing due to this exposure to air?
Yes, so we so NPL, we also have TOFSIMS experts. So a colleague of mine, Yundang, he took some of the samples using an air-free sample transfer mechanism, and he transferred them from the glove box to the TOFSIMS, and we're able to see which ions change as a result of even a very short air exposure and which ions don't change, so that we can sort of keep track of what ions are doing as a result of the even short air exposure.
And so what did you see?
So I have, there's obviously a lot of oxidation in general, and we see decrease. I can't remember exactly which signals, but there's a suppression of some signals as well after air exposure for even a short time. But I can't remember exactly which ions those were.
Okay, thank you.